So in this video, I'm going to be covering the mechanisms of two fairly important reactions in organic chemistry, and they both have to do with esters. All right. One is going to be what's called a Fischer esterification, and one thing you'll notice, note in a lot of reactions in organic chemistry is that they tend to be named after the individual that first performed them. So for example, there's what's called the Williamson ether synthesis. That's a really famous reaction. In fact, that's an example of an SN2 reaction, which we learned about earlier. But when you're making esters, this is called a Fischer esterification after the scientist that invented it. A Fischer esterification is when, as the name would imply, when you're making an ester. All right, and you do that by connecting a carboxylic acid and an alcohol. All right. Notice that we're going to use R and R prime here so that we can tell which parts of the original, where the original molecules end up in the product molecule. All right. A little bit later, and I'll skip ahead here, we're going to essentially be doing the reverse of this in a reaction called a saponification. All right. And that's when you essentially you're taking an ester and you're going to break it apart into what is essentially a carboxylic acid and an alcohol. All right, but we'll talk a little bit more about that later. All right, so this is the overall reaction for Fischer esterification. All right, so going through the mechanism. All right, notice in the mechanism here, I'm going to be using HA just as a generic acid. All right, so you need, and you'll notice here I've got H plus, which when you see H plus, what that means is it needs an acid. All right, I'm using a generic acid because you can use several different acids for this. For example, you could use sulfuric acid, but there's some other types of acids that could be used. So we're just going to use HA, where A is just generically the conjugate base of this acid. All right, so the purpose of the acid is that it first it's going to react with carboxylic acid. All right, one of the electron pairs on this oxygen is going to attack that the hydrogen or the H plus of the acid. These electrons are going to go onto the A, and that would make an A minus, and that's why you see this A minus here. That's what results when these electrons do that. So when that then makes a covalent bond between this oxygen and that hydrogen. All right, so we could share the resulting structure like this. All right, notice that means there's only one lone pair with a positive charge on that oxygen. All right, and then somewhere close by we're going to have the alcohol, which we'll show right here. And what's going to happen, so the purpose of that original step where this is would be considered protonating the carbonyl. All right, remember this is the carbonyl group of that carboxylic acid. So this is a protonated carbonyl. All right, the purpose of doing that is that it puts a positive charge on that oxygen, and it makes it so that essentially this carbon here is more electrophilic, because these electrons right here are going to tend to want to go onto the oxygen. All right, so these electrons are wanting to go onto the oxygen because there's a positive charge there, and that increases puts a slightly positive charge on that carbon group right there. So it makes it susceptible to a nucleophilic attack from this alcohol. All right, so these electrons are going to act as a nucleophile attacking that carbon, and these electrons go up onto the oxygen. And that's going to make, and I know that this looks like a fairly complicated structure, but this species right here. All right, so what then is, notice that in this structure the positive charge is now on this oxygen down here. All right, so what's going to happen here is that the A minus, and it doesn't necessarily have to be this exact A minus, but there's going to be some A minus floating around in the solution, and that can act as a base that can attack this H plus right here. And when that happens, the electrons that were in that bond are going to go on to that oxygen. All right, that then makes this structure right here. Notice there's no longer a positive charge on that oxygen because it's got the two lone pairs. all right? And then your HA, which, so when this occurs, that creates a molecule of HA, and so we are going to have some of that acid floating around, and the electrons from this oxygen attack that HA. These electrons go onto the A, making an A minus. All right, that makes this structure right here. And notice that we're now in a similar situation to what we were with the nitration reaction. This right here is set up to have water leave. All right, notice there's a positive charge on that oxygen, and you've got it's bound right here. So all we have to do for water to leave is these electrons right here in this bond to go on to this oxygen right here. All right, and to help that to happen, these electrons right here are going to come down and make a second bond right here. So overall, this carbon isn't gaining or losing any bonds. It's losing a bond here, but it's gaining a bond right here. All right, so that then makes this structure right here. All right, notice there's a positive charge right here, and then you're hopefully you're kind of getting familiar with this. The A minus can then abstract this H plus right here, allowing these electrons to go back onto the oxygen, and that's going to give us our desired ester right here. All right. So one thing I want to point out about this reaction is that notice that the overall balanced reaction right here, it's a reversible reaction. It can either go this way, or you could theoretically it could go this way. All right, so if our desire is to make the ester, all right, well, how do we make that happen if this thing is reversible? All right, so recall Le Chatelier's principle. All right, if you've got a reversible reaction, if you were to add something to one side, it wants to drive the reaction to the other side. All right. Alternatively, if you take something away from one side, it pulls it towards the side where things are being taken away. All right. So since it's reversible, there's two ways that you can drive it. Either you're going to use a lot of excess alcohol, or I should say, or removal of water. And in a lot of cases, you do both of these. All right. So generally, when you do this reaction, you're going to do two things. You're going to have a lot of excess of this alcohol. For example, you might have just use the alcohol as the solvent that you're doing the reaction in. All right. For example, if you wanted to make an ethyl ester, all right, that would require using ethanol. All right. And ethanol is a very common solvent. All right. Another thing that you can do to help out is to get rid of a product. All right. So if we have a way to get rid of water, then that's going to, if you pull away this product, that's going to drive the equilibrium in this direction. So anything that you can do to get rid of water would help out. And so sometimes, especially if this is a higher boiling alcohol, you might just leave your reaction mixture open so that when you're heating it, any water that gets formed might just become a vapor and float out of the solution. All right. So, so one other thing I want to point out is that just kind of keeping track of, asking yourself, is the acid a reactant in this molecule, like something that you would need a full stoichiometric amount, or is it just acting as a catalyst? All right. So another way of saying that is the acid consumed in this reaction? All right. Well, if we keep track of things, all right, we have an HA here, and it gets used in this first step of the reaction. All right. But notice we regenerate an HA here when this A minus grabs that H plus. All right. We then use an HA right here. But then in this last step right here, we regenerate it. All right. So notice that there's no net either consumption of this or production of this. All right. It's consumed, it's produced. It's consumed, and it's produced. So overall, it's not acting as a product or a reactant, and that's why when we're drawing the reaction right here, we just put the H plus over top of the arrow. And that's a common convention. When something is just acting as a catalyst, you draw it over top of the arrow. All right. Generally, you're going to if something was put down here, that would be a solvent. But if it's an actual reactant, something that would be consumed, like the alcohol is consumed in this reaction. All right. you draw that to the left of the arrow. All right. So moving on to saponification. All right. First of all, saponification is essentially the reverse of esterification. All right. And the reason saponification, or where it gets its most fame from, is that it's the reaction that's responsible for making soap. All right. In fact, the name saponification comes from sapo, which is Latin for soap. All right. So here's the overall reaction. You're going to take your ester and treat it with sodium hydroxide and water, and this would definitely be sped up with heat, but as you recall when we made soap, it doesn't necessarily require heat. So as far as the mechanism goes, all right, let's start with our ester right here. We've got hydroxide right here, and what's going to happen is that the hydroxide is going to act as a nucleophile, and it's going to attack the carbonyl carbon. All right, remember, what makes that possible is that this is a polar bond where the oxygen is more electronegative, so the electrons are, even under normal circumstances, are pulled a little bit more towards the oxygen, making a slight positive charge on that carbonyl carbon. All right, that's then going to make this species right here. And what's going to happen is that the electrons, one of the electron pairs on the oxygen, notice that there's 3 pairs. Once the pair goes up onto the oxygen here, comes down, that can then kick the electrons in this bond on to this oxygen. All right, that's then going to make that's essentially that cleaves this bond. It breaks that bond right there. So we now have this species right here, and you'll notice that is a carboxylic acid, and it seems like the reaction might want to end there. All right, but actually what's then going to happen is that when this thing leaves, that makes this product right there, and that's what you call an alkoxide. And all an alkoxide is that it's the conjugate base of an alcohol. All right, and that alkoxide is going to grab this H+, and these electrons are going to go onto that oxygen, and that's going to make these 2 things right here. All right. So when this reaction is done, this is what you would have left over. And if you wanted to, if we just took this, oops. All right. So if we wanted to, we could take the reaction mixture and just heat it up, and if the alcohol has got a low enough boiling point, it's going to evaporate, and what you would be left with is this right here. All right, so notice, even though I didn't put it in the reaction, that your source of hydroxide would be something like sodium hydroxide. So there would be some sodium ions in this reaction, and so when you evaporated off all of the solvent, you would actually make an ionic compound right here, and you would consider this the sodium salt of the carboxylic acid. All right, so and again, when you say the sodium salt, another way of saying that is that it would be the conjugate base of the carboxylic acid. So if we actually wanted the carboxylic acid, all we would have to do is treat it with a little acid, something like some hydrochloric acid in water, for example, and that would give us the carboxylic acid. All right, one thing I want to point out is just a little review of something that happened. So why is it that this reaction right here occurred? Why did this right here want to grab that hydrogen? All right, essentially, why doesn't the reverse of that occur? Why doesn't an electron here pair here take this hydrogen right here? And a way of describing that is just to go back and review this concept from acids and bases called pKa's. Right, the pKa of a carboxylic acid is about 5. Of an alcohol, it's about 16. So what that means is that comparing a carboxylic acid to an alcohol, carboxylic acid is the stronger of the acids. And remember, there's that relationship. The stronger the acid, the weaker the base. The weaker the acid, the stronger the base. All right. So if you've got these 2 things around each other, notice that the alkoxide is a strong base, the carboxylic acid is a strong acid, so that is the direction that the reaction would occur in.